Hello, my name is Weilin Deng. I'm from Saint-Gobain Research North America. Today I'm going to give a presentation on robust compression pads for batteries, simulation-driven design, and cyclic fatigue testing. This is the agenda I'm going to cover today. I will start with an introduction of the lithium-ion battery cell and explain why pressure and compression pads are critical for the battery performance. Then I will go through two exciting topics. The first one is our simulation-driven approach of compression pad design to create agile solutions for our customers. And the second is to discuss the resilient performance of our compression pads under demanding conditions. Finally, I will wrap up with the key takeaways from this presentation. So let's start. To begin, I would like to introduce some characteristics of the lithium-ion battery cells and see why pressure is important. Here are the two graphs showing the thickness change of the battery cells during normal charge discharge. As you can see, battery cells naturally breathe, which is expanding and contracting during charge discharge. And they also show swelling irreversibly over their lifetime. In the literature, as has been studied over a decade, it shows that the amount of external pressure on the cell has a direct impact on the battery cell life. As you can see, the right amount of pressure, around 20 to 40 kilopascal in this study, leads to a better cell retention in the capacity and achieve the longest lifetime. However, too much pressure or not enough pressure can cause the battery to fail much sooner. Therefore, our job is to design a material that provides this optional pressure to the battery cell in its entire life. So this is the primary job for the compression pads. In this schematic showing the typical design of the electric vehicle battery module to battery pack. This cell-to-cell or C2C pad sits between the cells. Its key function is to accommodate the cell volume change during the cell normal operations, while maintaining the optimum pressure, which I mentioned in the previous slides. So this is a dynamic job. As the cell charges and it expands, the compression pads will be compressed to absorb the stress and the deformation. And as the cell discharges and contracts, the pads must push back to maintain constant pressure. So the compression pads has to maintain the optimal pressure level to the cell over the whole lifetime. In addition, the compression pads also serves other key functions like reducing vibration and enhancing thermal and electrical isolation between the cells. Different batteries have unique different needs based on their cathode, anode, and electrolyte chemistries, as well as different casing design like pouch, prismatic, or other formats. There is no one-size-fits-all solution. For example, the pouch cell requires a relatively soft compression pads, while the prismatic cell needs a slightly stiff material. The solid-state battery needs a very stiff compression pads for their best performance. We can customize the compression properties of our product for different battery needs. The graph on the right shows the compression force diffraction or CFD values for a range of our foams at different compression levels, typically at 20%, 50%, and 70% compressed strength. Also shows the foam product including polyurethane foam and silicone foam that aims for the pouch cell and prismatic cell, and even for the advanced solid-state battery chemistry. Our product's unique properties, such as engineered mechanical cushioning and the low compression set, directly translate into custom benefits like managed cell volume changes, safer electrical operation, and maximize the battery lifetime. We often come across with a very common question from our customers. Uh, this is great, you have a good product portfolio, but can I have a suitable foam for our batteries, and can I have it quickly? To address this challenge, we can leverage our simulation-driven approach. This slide shows a real example from a major OEM. The customer gave us their design of their battery module, including 8 cells and 9 compression pads between those cells. They also specified a particular stress strain curves or domain we call the green corridor that is required for their battery cell. And they would like to have a compression pad to meet this specific green corridor. We first checked our existing products, PF100 and PF27. As you can see, the blue line for PF100 was too stiff at the very beginning, and the red line PF27 was closer but fell out of the corridor at a higher strength. Neither one was a perfect match, so we need to find a good solution in this case. In the past, this would mean many hours or even days of lab work to test and find a solution. But today, we can use simulation to address this challenge. We ask ourselves, what if we combine these two foams together in the battery module? By using our well-developed mechanical models of our product, we simulate various combinations of these two foams. As you can see on this plot, we quickly find the solution. A combination of, for example, 4 or 5 layers of PF100 combined with the corresponding layers of PF27, it fits perfectly inside the green corridor. So it shows that simulation was the critical tool that allowed us to find this customized solution very quickly. Our simulation capability allows us to expand the solution design space even further. We can combine different foam types like polyurethane foam or silicone foam, or even we can create a dual functional compression pads by combining a foam with a thermal barrier. These 3 graphs shows how the prediction curves from our simulation tools closely match the experimental data for those complex combinations. It demonstrates the accuracy and the power of our simulation tools for fast exploration and the customization of the product. We have digitalized this simulation capability in a user-friendly digital tool called Maxwell UV Tapes. Application engineers can input their modules specifications received from customer, such as the beginning of life and end of life gaps, or BOL gap and EOL gap in this case, as well as the associated BOL and EOL stress target in the box. And the tool will provide the compatible materials associated with the optimal thickness of those compatible materials. And it will show the corresponding stress strain curves, visually showing the mechanical properties of the compression pad that meet the specific target of the stress requirement. For example, to meet the input parameters shown here, the tool recommends PF 150 with the optimal thickness of around 3.47 millimeter thick for this specific requirement of the CTQ. The mixture tool also supports combination design of the compression pads. We can select two different materials. Showing the example is PL47 and TRP1000. Input the respective thickness, and instantaneously we can see the compression properties of each component as well as the combined materials in the graph. By varying the materials we select and by varying their thickness, we can design a compression pad with a specific compression property to meet customers' requirement. This digital solution is vital to accelerate innovation and significantly reduce development time and cost for our customization product to meet the requirement of the customer specific CTQs. So we have designed the tool to select a good phone to meet the CTQs, and we have done very quickly with the simulation. The next logical question from our customer is this product reliable under extreme conditions? So battery packs are designed to last 10 to 15 years. So this is equivalent to thousands of charge and discharge cycles. For example, for MMC chemistry cells, this is equivalent to 1,000 to 2,000 cycles, and for LFP chemistry, this is equivalent to around 2,500 to 5,000 cycles. And this cyclic compression are under a wide range of operating temperatures, from sub-zero to very hot temperature up to 60 or 70 degrees C. This cyclic compression under very temperatures demands resilient material to achieve good battery performance, because a resilient material can maintain consistent pressure support to the cells, ensuring a longer cell life and a better performance. In contrast, non-durable materials will lose their ability to provide pressure to the cell, leading to accelerated cell aging and failure. To prove this resilience, we have extensive in-house test capabilities to test our products. We do not just test our product once under compression. We can test it for compression set measurements for many hours and days. And most importantly, we can test our product on our cyclic fatigue machine at a full range of temperatures, which can simulate thousands of charge and discharge cycles of the battery cell. One of the most rigorous tests we performed is the 3,000 cycle constant strain cyclic compression at different temperatures, as schematically shown here on this graph. This test simulates the years of cell breathing and swelling that a compression pad must withstand, and we ran this test at 3 distinct temperatures, from minus 20 degrees C to room temperature and to 60 degrees C. In the next few slides, I will show you the testing results of this specific rigorous compression testing. This slide shows the testing results at 60 degrees C. The findings are remarkable. On the left, you see the 3,000 cycles of stress strain curves plotted on top of each other. They form a single clean line. We cannot actually see quite much difference. The graph next to it shows the first hundreds, the thousands, and the 3,000 cycle overlay. they are almost virtually identical. The maximum stress um, of the compression pads in each cycle are plotted in this graph. They remain almost constant. On the bottom left, we show the compression properties of the compression pads before and after cycling. You can see those materials demonstrate identical compression properties before and after the 3000 cycle compression. The material shows very good resilience in terms of cyclic fatigue. We also checked the thickness change of the materials before and after the 3000 cycle compression. The change is very minor. The material reduces 3% of its original thickness. At the room temperature, the story is the same. The compression curve remains unchanged through all 3000 cycles. The maximum stress remains constant, and the before and after 3000 cycles curve are again identical. We also see the thickness change is very minor, which again demonstrates the resilient properties of this material. Now, moving forward to the most challenging testing at the sub-zero temperature, minus 20 degrees C. At this cold temperature, we see the foam recovery is a little bit slower compared to the high temperature at room temperature. This is pretty normal for a polymer because at this cold temperature, it is close to the glass transition temperature. Viscoelasticity becomes more significant in this case. But look at the data. The maximum stress of the compression pads remains the same. And when we look at the compression properties of these compression pads before and after 3000 cycle at minus 20 degrees C, the compression properties are almost identical, meaning there's no damage of this material occurs during the cyclic fatigue testing. Again, this can be seen from the comparison of the thickness change before and after cycling. In this case, there's only 0.4% change in thickness. We have looked at the microstructure change of these compression pads under extreme conditions. Side by side, we can see the SEM images before 3000 cycle and after 3000 cycle. As you can see, the foam microstructure remains completely intact. The cells has not collapsed or damaged. So this is the physical proof of the material's durability. So this brings us to our key takeaways of this presentation. First, I showed that we can offer solutions tailored for different designs with customized compression properties for different cell formats and chemistry. And second, we can use advanced simulation capabilities for our product design, which enables rapid customization and reduce the development time of the product. And third, our products are proven to perform, showing true resilient performance under thousands of cycles and across extreme temperatures. This all demonstrates our high-performance foam product can deliver superior cushioning for the lithium-ion battery cells to achieve their longer lifetime and better performance. So this is the end of presentation. Thank you for listening.